We have one invited talk and two contributed talk. The first talk of the session is by Constantin Dalyac. The title of the talk from Pasqal, the title of the talk is Probing for Quantum Advantage with Neural Atoms.
All right, thank you very much. So first of all, I'd like to thank the organizers. I've actually never been to Japan before, so it's the first time, and I'm so happy to be here. I'm already very impressed by this country. So thank you for having us. And the title of my presentation is, as Mohammed said, Probing for Quantum Advantage with Neutral Atoms. So as you know, Pasqal is a company. So as a company, we have to look for value of our QPUs. And so what I'd like to do today is to show you a bit the types of problems that we're looking at and how we try to understand if there's any potential to get quantum advantage or not. And I'll show you some aspects which are negative and others which are positive. So first of all, I'll do a tiny bit of presentation about Pasqal. So this is our presence in the world today. So we have our headquarters in France, but you see that we also have other offices which are in dark green in Canada, in the US, Saudi Arabia, Korea, and then we have communities with which we work in all the other countries in brighter green, so Japan included, or India, or the rest of Europe. And we have today a team of more than 260 employees, more than 80 PhDs, and probably 100 engineers. So really the idea of this company is that we're trying to put together engineers and researchers to make sure that we can produce reliable industrial scale kind of QPUs. So maybe if you want to see a bit of roadmap as a company, this is how it looks like. So you see that we're a full stack company. So at the same time, we develop hardware, but we're also developing softwares and building up products. So as of today, the generations of QPUs we have, it's with 100 qubits, and we are starting to add Z addressability. You can see here how we're intending to increase the repetition rate, which is one of the caveats of this platform, is that compared to D-Wave, for example, or superconducting qubits, it's much slower. And then we also have an FTQC program. So this, maybe you've seen the papers from Harvard from last year, but the idea is that using atom shuttling and some high fidelity gates, we have an architecture for a scalable logical qubits. Then also, what's interesting is that we have different generations of devices. So as of today, the machine we have is called Orion Alpha. For now, there has been 500 hours of usage by users on this QPU, and it's done in our factory in France. But we're also starting to build in Canada, and we will probably be building other QPUs in other countries pretty soon. So also an important aspect is that we're trying to open source as much as we can. So as of today, you can already check out Pulsar, which is the language we use to code the devices. And then we have other solvers and emulators, which we will make public as soon as possible. An example of how these industrial, having engineers and trying to get industrial standards have helped is, for example, in boosting the number of qubits by doing two specific works by engineers, which is a fancy optomechanical bench for the atomic array creation, and then also a laser lock system, which enables you to precisely control the laser frequency. And using this, we were capable of doing arrays of atoms. So each point you see here is an atom. And we go up to 40 by 40 fluorescence atom array. And then we can even do some rearrangement of these atoms in given shapes. And we go up to 828 atoms. We're using this technique. So this is really one of the examples of using engineers to take ideas from the lab and make them a bit more reliable. So how does a neutral atom QPU work? The first way you can use it is in an analog mode. So here the idea is that you have a Hamiltonian, which you can program given some parameters, and then you're going to let the system evolve under this global quantum dynamics, and then you can measure your system and see what happens. The pros of this is that it's naturally implemented on a platform. So you just have to shine your Rydberg laser on your atoms, and voila, you have some dynamics. you have intrinsically high fidelity of your operations, and it's also pretty fast. It takes a microsecond to get your quantum states. The cons on the other side is that it's quite restrained, right? You cannot do whatever calculation you want, and it can be potentially harder to scale when you go up to 10,000, for example. But you can also use your neutral atom QPU in a gate-based control way. So we're all familiar with this, but the idea is that you can program your quantum circuits using your digital quantum gates. Pros of this, it's how a classical computer works. So you probably want to do that in a far future. And there's also a clear path with neutral atoms to prefer quantum error correction using some known techniques. Cons of this is that if you want to use it as of today, it's quite far away. And you also need extremely exquisite control of your atoms, which can be very hard to get from an engineer point of view. So let me talk about the analog version, and I'm going to explain how we use the many body interactions and control over the atoms to use quantum dynamics for specific problems. So here what you see is an array of atoms where they all start in a ground state, which we call the zero state as you want. And then you can address some transitions going from a ground state G to a Rydberg state R, which is a very excited state. And if you do this, the interactions become bigger than micrometers, which makes it possible for the two atoms to communicate when they are nearby neighbors. So here the distance is usually 5 micrometers, and using the Rydberg states, you can make them interact together. So the interactions you get is that the electron is now 1,000 times further away from the nucleus as it is in the ground state. And so you create a dipole because you have this negative charge at the end and this positive one. So you create a dipole, and these dipoles can interact together, usually on the typical micrometer scale. What you can do is 2 types, depending on the Rydberg level that you choose. There are many in your energy levels. You can either create some kind of blockade regime. So when you excite one atom, its neighbor cannot be excited. And you'll see that this is what we're going to use for combinatorial optimization. But then you also have very interesting flip-flop interaction. So here the excitation can actually be, you can actually see it moving across your system. And this resembles a lot quantum random walks, which can be also very useful. So once you have your interactions and you have some control over your atoms, so in time you can modify the parameters. Here it's called the Rabi frequency and the detuning over time. You obtain a state at a time t. Now, if you measure the system at the end of this, for example, here what we're trying to do is the antiferromagnetic preparation of this square lattice, then you get, with a given probability, either one or the other checkboard. And this, if you do a lot of samples, you get all these estimates. And here what you see is that you've prepared with quite high fidelity these 2 states which correspond to the ground state. Why is it nice to look at a near future to the analog mode? It's really because you're using your QPU in its most natural mode. So what I like to show is also one of the papers from Google from last year, where you see, which is called the thermalization and criticality on your analog digital quantum simulator. And what you see is that although they use the digital state preparation and then gates to do the extensive state characterization, in the middle, what they do is that they let the system evolve according to the quantum dynamics of the system. And so they get this high fidelity analog evolution. And if you look at the paper, so this is the mixed state entanglement you get compared to the effective size. This was what they had before without putting the analog part. And you see that this big jump in the fidelity of the quality of the mixed state entanglement probably comes from this step of doing high fidelity analog evolution. But it's not the end of the story, right? So Antoine Broes, co-founder of the company, they did an experiment where you can compare the magnetization. So you're preparing what I showed you before, so the antiferromagnetic state. And then you can measure experimentally these values, right? And then you can compare it to the MPS simulation. And what's interesting is that for 10 by 10, it takes across like 14 days to simulate it properly. And then experimentally, you can go to bigger system sizes, such as 14 by 14. And what I really want to mention here is that some people think that NISQ devices, if they're gates or analog, it's kind of the same thing. It's just noisy quantum computation. But I'd like to explain that it's not really the fact, right? So typically, because you can just let the system evolve with Hamiltonian, and with the digital way, you would have to to trotterize your evolution, and you would have a lot of gates. The idea is that if you let your analog mode evolve with an error level, which is only 1%, then if you wanted to do the same thing with a digital quantum circuit, you would need approximately 1 million gates with an error which is lower than 10 to the minus 6, if you wanted to simulate the same quantum dynamics. So this is really to show you that as of today, if you use a neutral atom QPU in the analog mode, you're already in a regime which is extremely challenging. But of course, the question afterwards is, what do you want to do with this? So these are the references of the numbers I'm giving. All right, so I'm going to start with common root optimization and how Ising Hamiltonian can be used to tackle these problems, and also known as the infamous maximum independent set problem on unit disk graphs, if you've ever come across them. So you can map a unit disk maximum independent set to neutral atoms. Just let me give you a bit of an explanation. We have the MIS problem, which is the following. You're given a graph with vertices and edges, and you want to find the maximum number of nodes which are not neighbors inside of the graph, and you want to make this set as big as possible. So here, for example, it corresponds to taking node 1, 4, 5. And you can, mathematically, you can represent this by having each node with a label ni, either 0 or 1. And then your space of solution is 0, 1 to the power of number of vertices you have, right? And the cost function you have is the following. So it depends on each single one of the labels. And what you want to do is this function, you want to minimize it. And so the idea is that if you put it in the independent set, then you have a -1 here for each node. So you're trying to have a maximum of nodes in this. But if you ever have two nodes which are neighbors in the graph, you have this huge penalty term, which is u, and u is much, much bigger than 1. So the idea is that the ground state of this cost function, or the lowest energy, corresponds to the maximum independent set of your graph. Okay, great news. With neutral atoms, what I showed you before, this is the type of Hamiltonian we have, and in units of h bar. So you see that you have a sum of sigma x with the term you can control in time, omega of t. Then you have this minus delta of t times the sum of the ni's, where the ni's is just the projector on the Rydberg states, so on the excited ones. And then you have this term, which is the interaction term between atoms which are in the Rydberg state. And this is quite close to the penalty term that you see right here. So the idea is that if I set omega to 0 and delta to 1, you see that I get rid of this term, and then I get this minus sum of ni, which is this one. And then I need to create this term, and you see that it's very close to this one. Now, you see here that there's a dependence in space. So it's 1 over r6, where r is the distance between two atoms. So if you want to represent properly the problem, you have to make sure that the atoms are placed in such a way that the interaction matrix that you get here, so the C6 over Rij6, represents truthfully the adjacency matrix of your graph. So if you do this, for example, on a triangular layout, it's actually one of the best layouts you can find for the atoms. And you see here, if I plot the interaction matrix, it's mostly 1 where there's an edge. So for example, between node 0 and 1. So I can't, so yeah, between 0 and 1. And then you don't really see the others, but there's a tiny bit of purple. I don't know if you can see it from far away. But the tail of the interaction is not really relevant here. So the takeaway message basically is that the solution to the unit disk MIS problem can be encoded in the ground state of your Ising Hamiltonian on neutral atoms. So people think, great. We've looked also at, this was firstly explained by Pichler in 2018, and then we explored how some industrial problems could be mapped to this, and we tried to look at the neutral, what it would look like on neutral atoms. Now, what I'd like to show you is now that we can do all of this in theory, but there's also practice. So what we did is that because the triangular layout works so well to represent the graphs, we took a triangular layout, and from this triangular layout, we generated a bunch of graphs. These graphs went from size 5 to 10, so all the evolution, you can do it, you can do the simulation exactly. So we had 30 graphs of these sizes. And then what we did was to try to see if can you find one pulse which works well on the whole family so that you can generalize afterwards to bigger graphs. So if you look at QAOA, for example, if you want to do this, and promise it's the only time I'm going to talk about QAOA, you can try to to find the best optimal parameters of your mixing time and your what I call the cost time. And what you see is here that this is the different minimums for each of the graphs that we have in our data set. And what you see is that you can't really find one zone which gives you good results, whatever the graph you have. Now, if you look at quantum adiabatic algorithm, we have this shape of a pulse. And then what we just want to change are these two parameters, which are the final detuning of our Hamiltonian and one in the middle. And what you see is that they all kind of regroup in the same zone, which is not so surprising because they have the same initial layout. And so we believe that the zone of MIS is more or less the same. So what we do now is that we train on these graphs, we train a pulse. And here what you see is, depending on these parameters, delta and omega, so this is the pulse in time that we apply, you have a probability of having the MIS. So we start from this zone, and the goal is to arrive inside of this zone exactly. Now what you see is that here there's kind of a big loop that happens. And you can wonder why we're not going straight through. And the reason is just that there's actually some very small values. There's an adiabatic gap, which is an energy gap, sorry, which is quite low. And so what our pulse is trying to learn is to go above this, but we have some constraints on the machine, and you can't go above 1. So it really just tries to go max to 1 and then come back and just not touch any of the very low values of the energy gap. And now that we have this optimized pulse on small instances, we tried to run them on bigger graphs of the same triangular lattice. And we actually went up to 100 qubits to do this. And this is one of the photos we have of the graph. So you see it's on triangular layout, but it's fully connected graph. So I didn't put the edges, but you can trust me on this. And then we plotted for each of them the probabilities of preparing the MIS, but we're also interested in low-lying states. So let me just take you through this figure a bit step by step. So here you have the graph sizes from size 10 to 100. And then you have two columns. The first one is some tensor network simulation that we do to estimate the quality of our preparation. And the next one is adding state preparation and measurement errors, which you always have on these kinds of devices. So what you see is that at size 10, in theory, you should have a very good probability of preparing the MIS. And if you look at the probability of the MIS, it still stays quite big when you reach size 100. But then in practice, it's the small rounds you have here. These are experimental points. And you see that they fit quite well the tensor network plus spam estimations. And what you see is that actually the MIS drastically drops down right here to right there to right there, right there. And then you can't really see it. And it's only 0.05% of finding the MIS at size 100. If you do exponential fits, actually, you can show that for simulations or in the experimental case, you can fit this with an exponential of -n being the graph size, over this constant, which is nk, where k is the MIS minus k that you're trying to look at. And you see that in simulation, the MIS, the nk simulation is 81, and then it drops down to 14 experimentally. This is without any post-processing, right? So you can always try to get back a bit further up. And then you can see the different values for the MIS. So these results are interesting because first we've shown that you can use a pulse which generalizes not so badly to big graphs. So we don't have to retrain the pulse, which is nice. But what you see is that there's clearly, if we go to 1,000 nodes, for example, the probability of the MIS is going to be extremely, extremely low. So you would have to do a lot of shots to find it. So we have the proof experimentally that we can tackle some MIS problem, which is interesting. But there's really a much, much more important question, which is, are these actually hard instances? Because if you take graphs on triangular layout, it corresponds to chordal graphs. And there's actually a polynomial algorithm to solve this classically. So, okay, it's a good proof of concept. But can we find the hardest instances possible for the unit disk MIS problem? And if we're capable of doing this, can we embed them on the device? So now I'm going to bring you through the quest of looking at this MIS problem and classical state-of-the-art algorithms. So we have these MIS on unit disk graphs. And as I said, it's encoded in the ground state of your Ising Hamiltonian. And other than triangular, there's also the King's lattice, which is the biggest instances that have been done on the Harvard machine. So up to sizes 289. But Sorry, yeah, and so the idea is that actually any kind of primitive of applications in optimization, it will use at some point the QPU to sample an MIS or some independent sets on graphs which are unit disks. So how complicated you do this scheme, if the essential brick can be done classically, there's no point in using your QPU. So what's interesting is that those King's lattice, they're supposed to be NP hard, but in practice, researchers have shown that you don't really see an exponential runtime in the instances. So this is King's graphs, and you see at size 2000, even for the hardest instances, you're pretty much under the few minutes to solve it exactly. So where are the hard instances hiding, and how can we do to bridge the gap between our QPU, which would take, for example, 10 to 100 seconds to find the solution, and your branch and bound algorithm, Cplex, which takes only 10 to the minus 1. So this graph was taken from Andres 23 for the reference. And the idea, and I think it's a bit what Helmut said in his presentation, is that you want to find a native benchmark problem that uses as many atoms as possible on your device, and also which is as hard as possible for the classical algorithm. So you're trying to bring this runtime this way, right? And then if you do better state preparation, better annealing protocols, maybe you can bring the QPU this way. So you're trying to close the orders of magnitude. So finding the hardest unit disk problems, what we do is that we use intuitions from complexity or results from complexity theory, and we look in practice what happens. So for example, there's a result, which is that if you have something which is called fixed thickness, which is related to the density of your graph, then the runtime of your algorithm to solve the MIS, it only runs linearly in the size of the system, but exponentially in this thickness. So what we wonder is maybe if we can increase the thickness of our graphs, maybe it will make the runtime slower of classical state-of-the-art algorithms. And when you look at theory, you get the following results. If you look at the density of your graph, so density would look like this, right? So you just put atoms, and then your density is given by the number of atoms you put divided by the size of the square in which you randomly pick them. And the idea is that it's pretty easy at low densities. You can solve it easily. It's also easy if it's extremely dense, because you can imagine that if it's extremely dense, there's only a few points which can make the maximum independent set. So from theory, we know that the hard instances should be hiding somewhere in there. So what we did is that we also did B&B numerics, and we did this for changing densities and graph sizes up to size 1,000. And for each of these points, we have approximately 100 graphs. And what we see is that there seems to be a kind of a harder phase where the graphs are a bit harder to solve. But our QPU today can go up to 100 qubits, and densities stop about here. So what you see is that as of today, on our QPUs, all the instances we can embed are actually easy instances. So maybe it's not that useful to try to solve this problem exactly. What you can try to do is, of course, increase the graph sizes, but you will also need to increase the density at the same time to see if there's an interest in using your QPU. All right, so what you can do is change the minimal spacing between the atoms, or you can also change the Rydberg level, which can artificially increase the density. What's interesting is that there's also hardware improvements, and then we wonder, okay, but these can maybe bring new graphs. What can we do with those new graphs? So for example, if I take this graph, I can add what is called Z addressing, and it's basically the same as adding weights to the graph. I can also do X addressing, and this corresponds to not having unit disk, but only disk graphs. And then finally, there's also possibilities of doing 3D registers of atoms, and then I'm not in a unit disk, but I'm in a unit ball setting, which is a bit more hard. But bad news, they all fall under theoretic efficient approximation schemes. And you can even mix all of them together. It's always easy to approximate. But we also wanted to see that in practice, right? Because theory sometimes can give you guidelines, but maybe in practice you can find something which is a bit harder. So what we managed to do is that we increased some instances. We're going to look at the Z addressing, and using weights, we managed to increase artificially the runtime, but only by a factor of 10. So it's something, but it's not enough if you want to close the 3 orders of magnitude gap. How we did this is the following way. So Cplex is a branch and bound solver, and it basically uses search and refutation by using an upper and a lower bound. And if those bounds are close together, it can solve the problem more quickly. So what we try to do is really to open the gap between the two bounds. And to do this, for example, we add weights on the King's lattice graphs, and we use a method called degree centrality. So you see here that the color corresponds to different weights, which are related to the number of neighbors they have. So what we're trying to do is to make the energy landscape more complicated. And you can see that for graph sizes, at the beginning, you don't really see the difference. So this green one is in the unweighted case. And if you add degree centrality, then you see that you can start gaining some order of magnitude. So theory tells you that it's maybe not the best place to look for an advantage. Numerics tell you that you can go at least a tenfold, but it's still not enough to get to the quantum methods on par with classical ones. And then there's another opportunity. There was a proposition to do quantum optimization with arbitrary connectivity. But there's a big problem that comes from complexity theory, which I'm going to explain to you right now. So there were some methods which were proposed. And the idea is that you can take any graph G with arbitrary connectivity, and then you can map it to a bigger graph G prime, which is a unit disk, and you put weights on it. But my question is, what happens when you get an approximate solution in this huge graph? And what I can show you is that if you can take a graph G, which is part of a complexity class called XAPX, these graphs are graphs for which you cannot guarantee an approximation ratio, which is better than exponential to the minus n, where n is the size of the graph. So as the size of the graph becomes big, the ratio becomes extremely small. And the unit disk graphs that we have, they actually have a super strong approximation scheme, which is called EPTAS, meaning that if you want to be epsilon close from the best solution, then you can do this in only polynomial time, in linear polynomial time of the system size, and also in the precision that you want. So this is extremely powerful. So if I have a graph G, which is kind of complicated and part of APX, and then I find a mapping to G prime, which now is a graph which is actually in this approximation scheme, well, theory tells me that if I use an approximate solution from here to find an approximate solution from G, it's not possible. Because if I had a good approximation, it would mean that I could apply this EPTAS to this graph. And so it would mean that this class XAPX is equivalent to this one. And unless P equals NP, this is false. All right, so this is complexity theory intuition. You can also see it from a physics point of view, is that the Hamiltonian of your graph G, what you want to do is map the ground state to the ground state of your augmented graph G prime. But then you have no way of guaranteeing that the approximate good quality solutions, they get mapped everywhere in the spectrum. So if you prepare a pretty good state, then you have no way of using it to find a good solution of HG. So we also did numerics of this, right, in practice. And this is what we show. So we took graphs, Erdős-Rényi graphs, of size only 28 with probability 0.4. And it gives you G prime, which are weighted unit disk graphs with 3,000 nodes. And if you do this, this is the graph you get. So here what I plot is when I take an approximate solution, what is the distance from the optimal solution? And then on the y-axis, it's if I use this solution to deduce a solution on the initial graph G, what's the quality of the solution I get? So the 0.00 means that if I find the ground state, I do get the ground state of G. But then as soon as I'm a bit far away from the optimal, I get into this regime. And these regimes, these bit strings, if you want to rededuce a solution, it's as good as using a completely random bit string. So the approximation does not hold. So gadgets, not a good idea. All right, I have 10 minutes left. So maybe I'll just jump to, no, I can go through this one too. So now I'm going to explain a bit something that we've done in graph features. So what the idea is that we want to use quantum correlations to enhance a bit of machine learning models. So you know that machine learning on graphs can be quite useful because a lot of data is under the form of graphs. So you have, for example, you want to do node link prediction. So for example, if you want to anticipate new partnerships, or if you have an electric grid, you can try to do clustering to do the segmenting of the highly connected zones. If you have a social network, you might want to do some community detection so that you can do recommendations to users which have the same type of community as other users. And then if you have molecules, for example, those also are very good graphs. And you can try maybe to do classification and predict, for example, the toxicity of compounds. Now, one of the most advanced methods for tackling problems with which are under the form of graphs are graph transformers. So the idea is that you have a graph, and for each of the nodes, you have some vector of features, and the edges can also have features. And what people have done is that they've added what is called positional encoding. So positional encoding is the idea of making better features to do your classification or regression task. And people typically use Laplacian eigenvectors or random walk probabilities. And then this is how you obtain your transformer model. So these are a few of the references you can look at if you're interested by these graph transformers. And what we've done is that we've proposed some quantum positional encoding. So instead of using the common classical positional encodings, which are the random walks or the eigenvectors of the Laplacian matrix, we tried two different things. So the first one is this positional encoding, and the second one here is the XY Hamiltonian one, and this corresponds to a quantum random walk. So if you look these synthetic graphs, so this is class 1 and this is class 0 and class 1, you can see that, for example, the RRWP, so the classical method, if you look at the positional encoding, they look very much alike. Whereas if you look at the quantum correlations that you have with the quantum walk, you see that you can really differentiate between class 0 and class 1. So the idea is that we've shown theoretically that some quantum correlations are more expressive than classical ones on a specific type of graphs, which are highly regular graphs, but at least it exists. So you're trying to enhance your model with this. This is an example of how it looks like. So this is a classical random walk, and you see that after 4 steps, these are the correlations that you get. But in the quantum case, you see the correlations are a bit different. So the hope is that you're capturing correlations which can be important to differentiate between your two graphs. And now what we're doing is that we want to run these on true data sets to see if it has an impact or not. But on artificial data sets, you already see a huge difference. Finally, I like to talk about amorphous solids. So when you're looking for quantum advantage of neutral atoms in the analog version, one of the very appealing things you can do is quantum simulation. Right? So this is a paper where they describe the idea that we have. So maybe you know, but there's crystals which have good qualities because they have translational invariance. So you can study them quite precisely. And then you have something which is called amorphous materials. So the idea is that in the neighborhood of a node, it's well defined, the number of neighbors you have. But if you de-zoom out of it, then you have no long-range order, whereas you really have it in crystals. So this has already been used to do, for example, these thin film solar films. And now there's some interests that are rising, trying to do this at the quantum level. So doing amorphous topological insulators, semiconductors, superconductors. And there's also some interest by the physics community on amorphous quantum spin liquids. So the idea is that these amorphous solids, we can actually represent them with the atoms. So these are 3 examples of graphs with different coordination numbers. So the coordination number is the number of neighbors you have when you're one node. They typically have 3 neighbors. These ones have 4, and these ones have. You can also choose something which is not an integer and have, for example, 3.5, and you will have a mixture of nodes which have 3 neighbors or 4 neighbors. Now, the idea is that you can consider then the antiferromagnetic Ising model, which is the one I showed you before, which we have naturally on the device. And what's interesting in those systems is that you can prepare at the same time some locally frustrated plaquettes and some which are not frustrated. And these coexist in your amorphous magnet. And so if you want to study this, even from a classical point of view, it's already some complicated energy landscape. So the whole idea behind this will afterwards be to study those with quantum fluctuations to see if the phase transitions of these magnets are interesting or not. And they're much closer to real-world structures. So for example, we can look at the classical glassiness of our system. So this is only a classical right understanding of these systems. So this is typically the profile you have when you look at the distribution of this structure factor. So when you're in a square, typically the square is unfrustrated, and you have these 2 peaks. So when you have two copies of your system, they are either completely correlated or completely anti-correlated. And then if you're in a Kagome lattice, which resembles a bit this one, then you have something which is a bit more complicated. So you see the correlations are around 0. Now, if we do the same thing with amorphous solids, on the left, what you have is an amorphous solid which has which resembles a square, but not really. So you see that it's kind of, you still have those peaks on the sides, but they're not perfect as in the square case. And this is for a Kagome version of it. And you see here that the spread is quite big. So when the spread is quite big, we have hard time finding the ground state of these systems classically. So already it's an interesting, we hope that it's an interesting system. And then what we're going to do, of course, is to study the interplay between those classical magnetic frustrations we see, which arise from the positions, where these frustrations comes from the positions, and then some quantum fluctuations when we add a transverse field. All right. To conclude and to summarize, in common optimization, it seems extremely tough to find some quantum advantage. And this is for numerous reasons. First of all, we've understood that locality, or the structure that you have in a graph, it can be harnessed by classical methods. And so they find optimal solutions in very short times. Furthermore, a quite important result is that even though there exist mappings for much more complicated combinatorial optimization problems, we believe that the approximations would never hold. And the problem is that on your QPU as of today, it's extremely tough to get to the ground state exactly, even though you can get good approximate solutions. For the amorphous solids, what's interesting is that the Hamiltonians already classically are hard to tackle. And we've been running tests using MPS, PEPS, neuroquantum states. And we're seeing that the Hamiltonian, the state can be extremely difficult to follow in time. So at the moment, we're continuously developing these state-of-the-art methods to see if, from a quantum point of view, it's hard to follow. So, of course, neutral atom is very nice to study the amorphous solids because you have a total flexibility on the layout, so you can really represent the structure of your crystal, of your amorphous solid, sorry, as you want. And then you have a lot of potentially interesting physics in this case, so you can look at spin glasses, of course, versus spin liquids, but there's also things like Griffith spaces. And finally, for graph machine learning, we've shown theoretically that there are some quantum features which are more powerful than classical ones. And this is only on a family of graphs, which are strongly regular graphs. But our hope is that we can find interesting data sets for which these quantum correlations are useful and help you find a good solution to your problem. All right. Yes, I said that. So finally, a photo of people at Pasqal. Extra point if you find me. And thank you very much for listening to this presentation, and I'd be happy to have your questions.
Any questions from the audience? Paul? Paul?
So maybe just a quick technical question. Earlier on, you said that your rep rate was like a hertz or something.
Yes.
But then after that, you said that the process takes a microsecond. So what is the bottleneck in terms of the rep rate?
Yes. So the quantum dynamics takes only a microsecond, but then when you have to prepare the system and measure it, you destroy the state of the atoms every single time. So you have to reload the whole bunch of atomic arrays, and this takes time. Of the order of, you can do one operation per second. So it's really annoying because you have this fast quantum processing dynamic, but then the rest takes a lot of time just to prepare the states.
Shimori-san?
I also have a small technical question. You said that you can simulate physics problem, including spin glasses and spin liquids and Griffith phases. And these are very subtle problems which needs precise control of interactions between neighboring disks. How much can you control the strength or the sign of the interactions between atoms?
Yeah, so the problem is that the sign of the interaction, you cannot change it. So they all have the same sign, so it's usually antiferromagnetic. And then maybe I can show you again, but the strength of the interactions depends on the distance between the atoms. So this you can control quite precisely, but then again, you're limited to 1 over the R6 types of interactions.
So then how can you simulate spin glass problems without the change of the sign?
So there's actually, if you have geometric frustration, you can create a glassy system.
In that sense, you can simulate frustrated system, not directly spin glass problems.
Yes, not all spin glass problems. Yeah,
okay,
absolutely.
Any other questions? Maybe I can ask one question. So you talk about making different graphs, but what I understood is you only can control the locations of the atoms, not the interaction, because interaction just falls off as power of 6. So how can you like design different graphs? I guess there's some, when the interaction is above some threshold, you call it like interaction otherwise.
Yeah, exactly. So you have a cutoff value where you decide that if the interaction strength or like the is strong enough compared to, for example, the omega you put on your system, then you consider it's an edge, and in the other case, it's not.
Okay.
But you can still map quite a lot of these unit disk graphs.
Okay. Any other questions? Okay, I can ask you one more. You talked about the position encoding. So in classical position encoding, you add a cosine or sine function to the vector representation of the nodes. And so do you do this by adding phase? How do you do position encoding in quantum?
So we just measure the correlations of the system.
Yeah.
And then we concatenate this vector of correlations. We just add it to the node features. And then all the rest is on with classical means. So there's no, if you want to add a minus sign, you can do it, but classically, like you're not doing it inside of the quantum correlation.
Okay, so the position encoding is done classically, not. I thought you add a phase to.
No,
Okay,
yeah.
all right, okay. Okay, if there's no more questions, we can move on to the next speaker. Let's thank the speaker again.